Hello and welcome to another lesson. So now that we have dealt with, well, I'll just go and review, writing symbolic statements in English and writing English statements as symbols, we can go ahead and talk about the individual truth values of each one of these pieces, or each of the simple statements inside the compound statements. So every statement, as we talked about before, can either have a true or a false state or outcome. So whether a compound statement is true or false depends on two things. One, the connectives used. That would be, and, or, not, for example. Or whether each individual statement is true or false. And that one is extremely important, of course. And all of these outcomes, these possible outcomes, we're going to summarize in tables called truth tables. So let me start with a bit of an example here. So what I've got here is, it doesn't look anything like your English circuits, your English statements, your symbolic logic, but it does the same thing basically. We have two inputs going into something that says AND on it, and then it says some sort of output. What this actually is, this is a connective, which is an AND connective. And these are our two inputs. We could say this is P and this is Q. So what it does is that when both of them are true, so right now they're both off, which means they're both false. If both of these are true, then the output will light up. So if this one is true, we can call it 1, we can call it on, and this one is true, you can see that the final output is going to be on. So this gate, this logic gate, only lets us put output from it if both things are true. So if this is a 1 and a 1, it gives a 1. If this is true and true, this gives a true. If this is, yes and yes, this gives a yes. But if one of them is false, the final statement will be false as well. And so it can be a little tricky to keep track of this, so we need to make what's called truth tables. So let me show you like a little foreshadowing of what we're going to do. If we called this our statement P and Q, and it's P and Q. So P and Q, what are all the possible states of the output? Because the output we can say is the final statement P and Q, this being our AND. So P comes in, and then Q. P and Q comes out as P and Q. Our truth tables look like this. We keep track of our information like this. We say, okay, well, they can both be on, 1 and 1. One could be on and one could be off. One could be off and the other one could be on, or they could both be off. Or we could call this true, false, like that. So in circuits, in logic gates, we use a lot of 1s and 0s, but right now we're thinking about actual statements. So they could both be true. It's cloudy and I'm cold. They could both be, one could be true, one could be false. So it's cloudy, I'm not cold. It's not cloudy, but I am cold. Or it's not cloudy and I'm not cold. But remember all the different truth values. This final answer here, because this is an AND gate, we only have the final statement true if both inputs are true. So if the first one's true, if it's cloudy and I'm cold, then we can say we have a truth value. Anything else, if one is true and the other is false, everything else is false. Another way of looking at that, let's just say I was looking at this circuit here. When they're both true, it should give on. So right now they're both off, or we can say they're both false statements going into AND. The final output is currently false. False, false, and false. If the first one is false and the second one is true, the final output is false. If the first input is true and the second output is false, second input is false, true and false gives false. But if they're both true, then we see that the AND gives us true in the end. So the most important thing about when we're dealing with an AND is that two trues give true. Nothing else gives a truth value here of true. We get false for everything else. So when I talk about logic gates, that's what I mean. The simulator or the logic thing that I just used was this. You should just click on that in your PDF, play around with it, try all the different gates, and, or, nor, all the other ones. See what you get. I'll come back to it later, I'm sure. So let's start with the easiest gate, which is called negation, or not. Also has the symbol of tilde, which is like a shift. It's in the top left of your keyboard if you have a standard keyboard. So negation changes the truth value of a statement to its opposite. So it's the exact same process as if we change a 0 to a 1 or a 1 to a 0. We're flipping it. It's the not. Or we flip a switch in a circuit. So you have a switch that's either on or off. Well, the opposite of on is off, and the opposite of off is on. What about filling in the truth table? Well, we always start, these are our inputs, right? This is our input. And the statement, if it has a connective, is one of our outputs. So if we input t, what are we going to get as our output? Well, we're going to get false, because the opposite of true is false. And if we input f or false, we're going to get true back. All right, so it's called a negation, or later on we'll see that it can also be called a complement. There are many words for it, but the ultimate process is that you just flip the input. So I've got another situation here with a slightly different program called Logically. So if you want to try this, I don't know if you can see the address bar, but it's logic.ly/demo, and you can try this yourself. This is a not gate. I pulled it over from here, not. It means negation. So currently this is a 0 or a false value. There's nothing going along. But when it hits the not gate, it turns on. If I was to start with an input that was on, it would turn it off. So it's the opposite. It's always whatever the opposite is. You can see if it's on here, it's off when it goes to the not gate. Of course, this is a circuit. This is more visual, but it works exactly the same as our situation in the notes. We put a true in, and we get a false out. You can see here this is called a not gate. And I'm trying to foreshadow for the next unit, which is a lot more about the gates themselves. But for now, let's just focus on the statements themselves. A conjunction is another type of connective. Conjunction means and it has this symbol, this little hat symbol. And one way I remember this is that and a really share, a similar shape. Look at the difference, or look at the comparison between and that. I don't even know what that's called, actually. It looks like caret, shift 6. But it's not. It's its own symbol. That's when you put two statements in. If one and the other is true, we'll get back an output. So let's talk about it like this. We just did it a minute ago. True and true gives true. True and false gives false. False and true gives false. False and false gives false. These are all the possible combinations of what I could get from an AND gate. There are no other possible inputs. If these are the inputs here, these are all the possible outputs. So something that you might want to keep in mind is that truth tables keep track of all possible input combinations. Just in case you were wondering, and there's, these are all the possibilities. For two inputs, there's always going to be 4 possibilities. Disjunction is a fancy word for or, and it has this V shape. So if it's not an and, it's usually an or. We'll see later that or looks like this, kind of like the Star Trek insignia, but we'll see that it can be thought of as a plus as well, but we will worry about that later. For now, disjunctions are true when either statement is true. Let me just jump back up here. I didn't make a big deal of this, I should have. Conjunctions are true only when both statements are true, which is why when both statements are true, we get our truth value out for the output. Similarly, disjunctions are true when either statement is true. True when either statement is true. One or the other is true. So true and true. Well, one or the other is definitely true in that case. So we have true and true. Of course we have true. In this one we have a true, and this one we have a true. The word true is starting to lose its meaning. But true or false. Remember, these are inputs. These are our outputs. If P is true or Q is true, we get true. So this is true, false or true, true, false and false. Now we have false. Okay. So the big difference here, as long as we see a truth value in there, as long as we see a true statement, that means the final statement's going to be true as well. And then this is our summary of basic truth tables. So our negation, our conjunction, and our disjunction. Try not to get them mixed up. Negation is our tilde. We'll see a not, which you saw earlier. Conjunction and disjunction or. Now I reviewed them as if we hadn't seen them before, but of course we've seen them before. Just in our last video, we have disjunctions, conjunctions, and negations all over the place. but I wanted to introduce it again in a way as a sort of review so that you had it kind of from two different angles. So that's our basic truth tables. Before I move on, little pro tip here. There are many good truth table and logic apps. Check out the App Store or the Play Store to see if you can find a good one to check your work. There's another really good website that I've got bookmarked here. It's a bit of a weird one. You can see, I don't know if you can see the address bar, but it's if you type in Logic Calculator Purple Monster or Logic Calculator Psychic Duck, or probably just Logic Calculator in general into Google, you'll find it. The whole point is that it deals with logic, and all you need to do is put in your inputs. So for example, let's just say we had P and Q, and we wanted to know what the truth table is. We can go P, and we can find our AND, or I think you might be able to use slash and the other slash. This is next to the shift key, and then you have your backslash. So I think you can deal with that, but I'm not sure. I'm not gonna tempt fate here. P and Q. And if you want the truth table, just press enter. And it will give you P and Q, true, false, false, false. And you should know that that's because we have two. If we have both true, gives the final statement to be true. If it's or, maybe we wanted to change it to an or. Press enter on that. P or Q, this is our final answer. So this can be really helpful for checking your work. Eventually we're going to be doing a lot of statements kind of in a row, and we'll use a lot more symbols, as you can tell. But it's good for getting an overview and double checking your work from start to finish to make sure it's all okay. All right, let's move on to some actual more practice with these truth tables. The first question here says, complete a truth table for not P or Q. So let's just be clear here. This is a not, and then this is or. So we need to set up the table. And what you should notice first is that there's two connectives. So if there's two connectives, generally speaking, we should have two columns for the outputs. What I mean is you'll have one column and you'll have a second column because we want to do our connective step by step. So it says do each connective one after the other. And you might wonder why I'm saying that. Well, it's because I'm not always going to give you the columns to fill in yourself. You're going to need to do that yourself. So P or Q, you can't get not P or Q until you know what P or Q is to begin with. So we need to get P or Q, and then in our second step we can negate it. All right? So P or Q. P or Q has a truth value of true as long as one or the other is true. So this is true, 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 and false. And again, if you're wondering why that is, it's because one or the other needs to be true, and in this case we have it. So as long as we see a truth value, I keep saying truth value, but as long as we see a true result, we're going to get true. Okay? And now what we can do is we negate it. Remember that this is P or Q. Well, now we're going to negate P or Q. So I probably could have done this earlier. P or Q, and we're going to negate it. So you take the value that you saw in 1 and you negate that. So false, 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 true. We're taking our value of 1, and really you could probably think of it like this. This is not column 1. So we have column 1 here, and the second statement there is not column 1. And it's the complete opposite of everything. So that's probably the easiest possible example I could give you. It doesn't get any more simple than that with compound statements. Like, that's the simplest two connective question I can give. So let's move on and see if you can try another one. I recommend that you pause the video and see if you can set this up yourself, because there's a lot of missing information. There are 3 columns. That's because we see 1, 2, 3 connectives. So if we have 3 connectives, we should probably have 3 columns. It's a good idea to do it that way. And we're missing all of this, all of our inputs. So let's do it in a systematic way. The first one is going to be half true and half false. And then the next, it'll alternate true, false, true, false. And if you do it that way, you're going to be able to get every possible combination. You can do this in any order you want, but it's a really good idea to just follow my pattern because it'll make sure that all of our work is similar. And it's a lot easier for me to mark. It's a lot easier for you to think through my work. So it's a good idea. What do we need to do? Well, we need ultimately not P and not Q. So that's going to be our final result. But we can't get there until we have the individual pieces. So you can't get not P and not Q unless you have not P and not Q on their own. All right, hopefully that makes some sense. So once again, let me label these. This is not. This is and, which means they both need to be true. And this is not. All right, and let's just start filling this in. Not P, well, take this column and negate it. Do the same thing for not Q. Take that column and negate it. Cool. So now we have, almost everything we need. Maybe I should keep those there. That might help you for later. We have not P and not Q. Or in another way of looking at it, you can think of it as if this is column 1 and this is column 2, we're taking not P and not Q. So take the results here and say, well, are they both true? Because that's really the final result we need. False and false. Are they both true? No. Just look down through and say, this is how I look at it. Are they both true? Is this both true? No. Is this both true? No. Is this both true? Yes. So actually, I would probably start there normally, and then I know the rest must be false because that's actually the only case where and gives a result of true. Okay, so remember, and is only true when both inputs are true. Otherwise, it's false. So maybe that's being kind of saying the same thing twice, but it's important to note. Otherwise, it's false. So that's why we have these false values, because not the inputs going in are not all true. Okay, so hopefully it's starting to make a bit of sense. There are many ways to approach this. I'm trying to give you the way that I feel is the most logical or sensical. So this is a bit of a crazy looking one. Complete a truth table for P and not Q, or not P and Q. So this looks very complicated, but if we do it step by step, it actually is not that complicated at all. I know my final statement needs to be this whole result. Okay, so this is what I would do first. And then at the individual pieces, maybe we should count how many operations. We have 1, 2, 3, 4, 5 connectives, which is why we have 5 columns. Because again, we want to do it sequentially, step by step in a logical way. P and Q, again, are our inputs. So true and true, true and false. False and true, false and false. That's all the possible combinations that we can have for this kind of binary setup for each statement. And now it's a bit up to you which one you want to start with. I just like to go from the left to the right, and I would say, well, we have P and not Q. I can't do that until I know what not Q is. So I'm just going to go ahead and do not Q first, and maybe work from there. So not Q is false, true, false, true. Again, just taking Q and negating it. What else can I do? Well, now I can do P and not Q. P and not Q. Because P and not Q is P and not Q. Just take the values T and F. Remember, and they both must be true. So in this case, I have a T and a T. They're both true. So that's when I get my true statement out of this. All the rest have at least one false. So they all come out to be false. I can't do P and not Q or not P and Q unless I get the other bracket taken care of here. So that's what I'm going to do next. So again, I need not P. That's pretty easy, just negate the column P. Next, I need to get not P and Q, because that's the whole bracket, and I can see that I have not P already, and I have Q, it was given in the question. So not P and Q. So where are we going to look? We're going to look, if we want not P and Q, I'm going to look at this one and this one. So try not to get too overwhelmed here. Just try to keep track and you'll be fine. Not P and Q. So in that case, I'm just looking for two truths. I see two truths here. Not P and Q. This gives us our truth value, and the rest are going to be false. I'll go through that more sequentially. Not P and Q. Are they both true? No. So I get a false. Let's do the next one. Not P and Q. False and false. They must be both true. So, all right, they're not both true, so I get a false. Not P and Q is true and true. Well, true and true gives a true, so I get the true here. Finally, T and F. Well, they must both be true to be true, so I get my false out of this. So hopefully I'm not overwhelming you too much with different notation. I'm trying to make it more clear, not less clear. Okay, and our final statement looks crazy, but again, it's not that bad. Because we have this, which is just this part of the statement, or this. Maybe I'll keep the colors. This is, we can call column 1. This could be column 2, which means that this is column 1 or column 2. So one or the other must be true for the final answer to be true. So we have this or this. Are they both true? Or, sorry, is one true? No. So false. We have this or this. One of those is certainly true, which means I get a true value out of it. I guess I could make it a fancy color. Let's just make it, I don't know, purple, because I have a true and a false. When you look back on this, it might be confusing, but it's good to watch the video again, and then you'll probably be set up. And now we have false or true. One of those is true. Oh shit, so sorry. This is supposed to be true. Yikes. True or false. One of them needs to be true. One of them is true, so it's true. Same thing here. False or true. One of them is true, so the final statement's true. And finally, false or false definitely gives a false. So that's why that comes out to be the way that it is. Okay, I'm just going to clean up some of the highlighting here. So I removed some of the highlighting and added more. But anyway, take a moment to look at that table. I definitely recommend that you rewind it if you are confused by it, because it's important that you get a good concept of how this works. But in the meantime, let's check the work. I've got this calculator in the back. So we have P and Q. Well, let's put in the full statement and see if our final answer is correct. So bracket P. Oops. Probably click on the website, shouldn't I? Bracket P and not Q. Close bracket. Or not P and Q. Close bracket. I'm going to hit enter on this. My final result should be false, true, true, false. And you can see here that it is false, true, true, false. It doesn't show you any of the steps, although you can. You can show the steps. It just looks a little bit crazy to write it like this. It can be a little bit confusing. But you can see that our results are in there. False, true, false, false. False, true, false, false. I see that in there. False, false, true, true. False, false, true, true is in there too. False, false, true, false. False, false, true, false is there. But again, you want to be absolutely sure of how this works. And the way that it's saying that not Q is false, true, true, which is what we can see in our case. P and not Q is false, true, false, false. So you can't do that. You can't do this one until you've already done the not Q. So it looks sequential, but it's not. If you want to write it like this on the page, that's perfectly fine, but I always break it up into tables because I find it's kind of easier to process in a linear way. But once you get really good at this, this might be all you need to make sense of all your work. So it's up to you how you want to approach it and how you want to solve it. But for now, maybe follow my method until you get a good grounding. All right? And that's it for this topic, because this is a bit of a dense topic. I want you to have time to process it. I recommend that maybe while you're watching this, because it's only a short video, go into these links, check them out, play around with them, especially the logic gate simulator. Like I really recommend that you try that logic gate simulator. This is one of them. I'd recommend you check out another one as well. It's logic.ly /demo. That's probably my favorite logic simulator because it's very visual. That's the one, I probably still have it up here. Yeah, that's this one. And let me just show you one more, just for the sake of showing you how these work. For example, you have an AND gate. What should we get out of AND? Well, they both need to be on, right? So I like this one because it's very visual. If one is on, but they're not both on, we get nothing. And you can see that power is trying to go through, or there's a truth value coming along this line, but it doesn't give us anything unless it's both true. Same situation, same story for an OR. So if one or the other is true, then the final answer is going to be true or on. So one or the other. So if they're both off, it gives off. But as long as one of them is on, I'm good. I'm good to go. And if they're both on, of course, I'm also good to go. Now you'll see that there's other situations. There's NAND, there's NOR, there's XOR, there's even XNOR, and there's some crazy tri-state. We're not going to cover every single one of those, but I just wanted you to know that this exists, and you can have a bit of fun with this. Fun is relative, depending on how much you like math, but you can enjoy it. And I recommend also that you look online for logic apps. Check the App Store, check the Play Store, type in Truth Table, type in Logic Simulator, type in Logic Game, and there's loads of resources to help you understand this stuff. And definitely check this IXL practice. It's just a good way to get a good handle on this. So the next topic we're going to cover is the other truth tables, NAND, NOR, and XOR, but we'll leave that for another video. I just want you to know where we're headed. That's it for today's video, and have a great day. We'll see you in the next lesson.